In the YouTube video titled Lecture 2, Modular Arithmetic and Historical Ciphers by Christof Paar, Professor Paar introduces the fundamental concept of modular arithmetic, a specialized form of arithmetic for finite sets. He underscores its significance in the field of cryptography, emphasizing that nearly all modern cryptographic algorithms, including historical ciphers like the Caesar cipher, rely upon this principle. Professor Paar initiates the lecture by providing a brief overview of cryptography's nature and its crucial role in safeguarding information. He then delves into modular arithmetic, defining the modulus operator and the concept of equivalence classes. The video presents practical examples, such as a clock and a bakery, to illustrate these core concepts. Subsequently, Professor Paar introduces the notion of rings, a more complex algebraic structure that provides a structured framework for performing modular arithmetic. He points out that rings are widely employed in various mathematical domains, including cryptography. The lecture concludes with an examination of historical ciphers, focusing on the Caesar cipher. Professor Paar elucidates the Caesar cipher's mechanism and explores techniques for its decryption using frequency analysis and brute force attacks. He then highlights the paramount importance of integrating modular arithmetic within cryptographic systems to enhance their robustness against cryptanalysis. From 0 minutes to 5 minutes of the video, Professor Paar begins by briefly revisiting the image discussed in the previous lecture, setting the stage for the current lecture's focus: end-to-end encryption and decryption. He emphasizes the importance of understanding finite sets, a fundamental concept in modern cryptography. He then succinctly articulates the lecture's objective: to delve into modular arithmetic, a key component of contemporary cryptographic algorithms. Professor Paar then illustrates the concept of finite sets using a familiar example, the clock, where a 20-hour time difference from 12 o'clock is reduced to 8 o'clock in the morning. He explains that this is because a clock represents a finite set with only 12 numbers. He further elaborates that visualizing finite sets as a circle is a useful approach, as it reflects the centuries-old understanding of time as a cyclic process. From 5 minutes to 10 minutes of the video, the speaker delves into the fundamental concept of modular arithmetic, a cornerstone of modern cryptography. The speaker employs a relatable analogy, the familiar face of a clock, to illuminate the cyclical nature of modular arithmetic. Adding 20 hours to 12 o'clock on a clock results in 8 o'clock, illustrating that modular arithmetic operates within a closed system. This fundamental principle is formally defined using the congruence relation. A is identical to R mod M, where A represents the number undergoing reduction, M denotes the modulus, and R signifies the remainder. To determine the remainder, the speaker explains 1 divides A by M and isolates the residual value. For instance, when A equals 13 and M equals 9, the resulting remainder is 4. A critical point is then emphasized: the remainder is not inherently unique. The speaker illustrates this with the example of 42 is identical to 6 mod 9, and also 42 is identical to -3 mod 9, demonstrating how a single number can possess multiple remainders within the framework of modular arithmetic. The speaker then introduces the concept of equivalence classes, sets of numbers that are considered equivalent to each other under a specific modulus. Using modulo 5 as an example, the speaker illustrates that the set -8, -3, 2, 7, 12 constitutes an equivalence class, where all elements yield the same remainder upon division by 5. This concept highlights the existence of multiple representations for a number within modular arithmetic. The speaker subsequently underscores the vital role of equivalence classes in cryptographic systems, particularly in asymmetric cryptography. The speaker stresses that modular arithmetic is indispensable for performing complex computations with exceptionally large numbers. The speaker illustrates this with an example from web browser security. When a secure connection is established, modular arithmetic is invoked for exponentiation using large numbers, involving calculations like 13 by 16 8 mod 5, resulting in a remainder of 0. However, the speaker cautions against utilizing the naive method of directly calculating exponentiation and then extracting the remainder. Instead, the speaker advocates for a more sophisticated approach that leverages equivalence classes to simplify these computations. From 10 minutes to 15 minutes of the video, Professor Paar introduces the concept of modular arithmetic, emphasizing its significance in modern cryptography. He underscores the importance of finite sets in cryptographic operations, contrasting the infinite sets encountered in traditional mathematics. To illustrate this, Professor Paar uses the familiar example of a clock, a finite set with only 12 hours. Modular arithmetic, he explains, involves adding numbers and then determining the remainder after dividing by the modulus, thereby ensuring computations stay within the bounds of a finite set. Paar provides the example of a bakery to further demonstrate this concept, highlighting the impossibility of acquiring an infinite number of rolls. A request for 12 rolls followed by another 20 would result in a total of 32 rolls, not 8, reflecting the practical limitations of a finite set. From 15 minutes to 20 minutes of the video, Professor Paar delves into the concept of modular arithmetic, elucidating its significance in modern cryptography. He emphasizes the importance of finite sets in cryptographic operations and contrasts them with the infinite sets encountered in traditional mathematics. Using the familiar example of a clock, he demonstrates that calculations in finite sets often involve wrapping around, where exceeding the set's limit results in a return to the beginning. To illustrate this, he shows that adding 20 hours to 12 o'clock results in 8 o'clock, not 32:00, because the clock's 24-hour cycle dictates a return to the beginning after reaching 12. To calculate the remainder in modular arithmetic, one must divide the number by the modulus and take the remainder. For instance, 32 mod 24 equals 8 because 24 fits into 32 once with a remainder of 8. He formally defines the modular operator as A is equivalent to R modulo M if M divides a minus R. Professor Paar then explores the non-uniqueness of remainders in modular arithmetic. He uses 42 mod 9 to illustrate this, showing that the remainder can be 6, 42 minus 36 is equal to 6, or minus 3, 42 minus 45 is equal to minus 3. From 20 minutes to 25 minutes of the video, Professor Paar elucidates the concept of remainders in modular arithmetic by employing a familiar example, the clock. He articulates that when adding 20 hours to 12 o'clock, the resulting time is not 32:00, but rather 8 o'clock. This result arises from applying the modular operator, which determines the remainder after dividing 32 by 24, the modulus. Professor Paar underscores the fundamental importance of this modular operator in the realm of modern cryptography. He then provides a more rigorous definition of the modular operator, stating that two integers are considered congruent modulo a specific modulus if their difference is precisely divisible by the modulus. The professor proceeds to demonstrate the calculation of remainders by dividing a designated number by the modulus and identifying the residual value. For instance, in the example of 42 modulo 9, the remainder is 6, as 42 divided by 9 yields a quotient of 4 with a residue of 6. He further exemplifies this principle using a larger number, 42, and a modulus of 9, again obtaining a remainder of 6. From 25 minutes to 30 minutes of the video, the speaker elucidates the concept of equivalence classes modulo 5, employing an illustrative example with the integer 12 and the modulus 5. They demonstrate that 12 is congruent to 7 modulo 5, as the difference, 12 to 7, is divisible by 5. The speaker then proceeds to construct a tabular representation encompassing all equivalence classes modulo 5. They emphasize that these equivalence classes contain an infinite number of members while concurrently acknowledging the existence of integers not belonging to any of these classes, such as the number 7. To further explicate this notion, the speaker introduces the integer 7 into the equivalence class initiated by 2 modulo 5, extending the sequence of elements in increments of 5. From 30 minutes to 35 minutes of the video, Christof Paar delves into the concept of equivalence classes in modular arithmetic, employing the illustrative example of modular arithmetic modulo 5. He elucidates how integers such as 2, 7, and minus 3 are deemed equivalent within this modular system due to their mutual difference of 5. This equivalence relation signifies that all members within a particular equivalence class exhibit identical behavior modulo the specified modulus. Paar then presents a pair of inquiries. 1. Ascertain the cardinality of the equivalence class modulo 5 initiated by 0 and 2. Determine if this set encompasses all integers. The first question is resolved as infinite, owing to the infinitude of numbers expressible as multiples of 5. The second question is answered negatively, as integers like 7, 8, 9, etc. fail to be multiples of 5. To address this, he introduces a second equivalence class commencing with 2, reiterating that this class, 2, possesses an infinite number of elements. Paar subsequently explores the third class initiated by 1, demonstrating that it comprises integers like 6, 11, and -4. Finally, he arrives at the conclusion that these three equivalence classes collectively account for all integers. From 35 minutes to 40 minutes of the video, the speaker introduces the concept of equivalence classes, emphasizing their importance in modular arithmetic. Using the example of modular arithmetic with modulus 5, he demonstrates how numbers like 2, 7, and -3 are considered equivalent. He posits that all elements within the same equivalence class exhibit analogous behavior when subjected to modular operations. To illustrate this, he employs the calculation 13 by 16 8, demonstrating how it can be simplified by substituting equivalent class representatives. Instead of using 13, he utilizes 3, as 13 is equivalent to 3 modulo 5. Similarly, he replaces 16 with 1 and 8 with 3, given their equivalences modulo 5. This substitution results in the simplified calculation 3 by 1 3 modulo 5, which is significantly less computationally demanding than the initial expression. From 40 minutes to 45 minutes of the video, Professor Paar delves into the practical applications of modular arithmetic in number theory, demonstrating its relevance in cryptographic algorithms. He employs the illustrative example of 13 by 16 8, resulting in 200. The objective is to reduce this value by the modulus 5. Professor Paar utilizes the modular operator to calculate the remainder, which involves dividing 200 by 5 and determining the residue. In this instance, the remainder is 0, as 5 divides 200 evenly 40 times. Hence, 200 mod 5 equals 0. Professor Paar then underscores the significance of adhering to the convention of selecting the smallest positive number during modular arithmetic computations, as this streamlining technique optimizes efficiency. He further introduces the concept of an inverse, a numerical entity that, when multiplied by the original number and reduced by the modulus, produces 1. This operation, although computationally complex, holds paramount importance in the implementation of cryptographic algorithms. From 45 minutes to 50 minutes of the video, the speaker delves into the realm of asymmetric cryptography, elucidating how modular arithmetic forms the cornerstone of most asymmetric cryptographic schemes. He highlights that exponentiation constitutes a prevalent operation within asymmetric cryptography, often involving exceedingly large operands, thereby rendering computation computationally demanding even on modern high-performance computing platforms. He then introduces the conventional, yet computationally inefficient, method for modular exponentiation, commonly referred to as the dumb way. This approach entails first performing exponentiation and subsequently reducing the resultant value modulo the desired integer. For instance, when calculating 3 raised to the power of 8 modulo 7, the conventional method requires computing 3 to the power of 8, yielding 6561, followed by dividing 6561 by 7 and obtaining a remainder of 2. This technique, however, proves to be computationally burdensome when dealing with substantial numerical values. From 50 minutes to 55 minutes of the video, Dr. Paar delves into the concept of equivalence classes within the framework of modular arithmetic. He emphasizes the fundamental principle of compressing an infinite set of integers into a finite set, thereby simplifying operations. This compression is exemplified by modular 5, where the integers are categorized into 5 distinct equivalence classes: 0, 1, 2, 3, and 4. Each class comprises an infinite number of members, all of which exhibit equivalent behavior within the context of modular 5. To demonstrate the practical relevance of this concept, Dr. Paar presents a hypothetical cryptographic system. He presents a computation, 13 by 16 8, which yields 200. However, when operating within the realm of modular 5, it becomes necessary to reduce 200 modulo 5. This entails dividing 200 by 5 and identifying the remainder, resulting in 0. Dr. Paar underscores that while multiple methods might lead to the same result in modular arithmetic, the standard practice is to utilize the smallest positive remainder. For instance, although 40 mod 5 also equals 0, the convention mandates the selection of the smallest positive remainder, which is 0. This practice is consistently adopted in various cryptographic systems. Furthermore, Dr. Paar elucidates that modular arithmetic's applicability extends beyond integers, encompassing other algebraic structures such as polynomial rings or matrix rings. These structures provide alternative algebraic interpretations. Dr. Paar concludes this segment by emphasizing the critical importance of mastering modular arithmetic in preparation for subsequent topics in cryptography. He underscores that the latter portion of the lecture will delve into asymmetric cryptography, a field heavily reliant on the principles of modular arithmetic. From 55 minutes to 60 minutes of the video, Christof Paar transitions from a practical, number-theoretic perspective on the modular operator to an exploration of its algebraic implications. He introduces the concept of a ring, a more complex algebraic structure than a group, which comprises a set of elements and two operations, addition and multiplication. Paar emphasizes that these operations are associative, meaning that their order of execution does not affect the result. He then focuses on the crucial property of closure in rings. This property dictates that any result obtained through addition or multiplication within the ring remains an element of the ring's set. He reinforces this point using the example of modular arithmetic with a modulus of 24. When adding two elements, such as 12 plus 20 is equal to 32, and applying the modular operator, 32 mod 24 is equal to 8, the result remains within the ring's defined set of elements. Paar subsequently explores the notion of an inverse element in rings, analogous to division in traditional arithmetic. However, he emphasizes that this operation is not always feasible within rings. A simple test determines the existence of an inverse for a given element, the greatest common divisor, GCD, of the element and the ring's modulus must equal 1. Paar elaborates that if the GCD is not 1, then an inverse element does not exist for the given element within that ring. This understanding highlights the inherent limitations of operations within a ring. The video concludes with Paar addressing the key space within the AINE cipher. He explains that the key space, which encompasses all potential keys for the cipher, is larger than the simple Caesar cipher due to the use of two keys, A and B, instead of just one. He calculates the size of the key space as 312, obtained by multiplying the number of possibilities for A, which is 12, by the number of possibilities for B, which is 26. 312 is equal to 12 asterisk 26. From 60 minutes to 65 minutes of the video, Professor Paar delves into the significance of modular arithmetic in the field of modern cryptography, with a particular emphasis on equivalence classes. He utilizes the familiar concept of a clock to elucidate the modular operator, emphasizing that the remainder serves as the pivotal element in this operation. To formalize this concept, he introduces the formula for calculating the remainder R, when given a number A and a modulus, MA equals Q asterisk M plus R. To illustrate, he demonstrates that 13 mod 9 equals 4 because 13 is equal to 1 times 9 plus 4. However, he underscores that the remainder is not inherently unique and provides multiple examples to illustrate this point. For instance, with the equals 42 and M equals 9, he demonstrates that the remainder can be either 6, 42 is equal to 4 times 9 plus 6, or minus 3, 42 is equal to 5 times 9 3. Paar then introduces the concept of equivalence classes, which are essentially sets of numbers that yield the same remainder when divided by the same modulus. To illustrate this idea, he uses modular arithmetic with modulus 5, demonstrating the existence of 5 distinct equivalence classes, each encompassing an infinite number of members. These classes include 0, 5, 10, minus 5, minus 10, or 1, 6, 11, minus 4, minus 9, for example. Although the members within each equivalence class exhibit similar behaviors, Paar highlights the importance of considering all potential remainders to avoid overlooking potential solutions. Paar proceeds to demonstrate how modular arithmetic can be leveraged to simplify complex computations within cryptographic systems. He showcases that any member within an equivalence class can be utilized to obtain the accurate result. For instance, he demonstrates that 13 by 16 8 is equivalent to 3 by 1 3, which is further equivalent to 8 to 6 minus 7, when operating within the context of modulus 5. This effectively illustrates how employing these equivalence classes can significantly simplify intricate calculations within the cryptographic realm. From 65 minutes to 70 minutes of the video, Professor Paar delves into the fundamental concept of equivalence classes within modular arithmetic, a critical component of modern cryptographic systems. He employs a familiar example, the cyclical nature of a clock, to illustrate the principle of modular arithmetic. This involves reducing any number to its remainder after division by the modulus, which is represented by the clock's hour hand, returning to 12 after reaching 12. Professor Paar then formally defines equivalence classes, emphasizing that numbers belonging to the same equivalence class are considered equivalent modulo the chosen modulus. He proceeds to illustrate this concept through concrete examples, demonstrating that numbers like 2, 7, and -3 are all equivalent modulo 5, as they share the same remainder, 2, when divided by 5. He emphasizes that within the same equivalence class, all numbers are functionally equivalent, meaning that any operation performed on one member of the class will result in a number that is also a member of the same class, despite potentially having a different numerical representation. This concept is crucial as it allows for efficient calculations in cryptographic systems. Professor Paar reiterates the importance of these concepts for both historical and modern cryptography, demonstrating how they provide a foundation for building secure communication systems. His examples provide a compelling illustration of how modular arithmetic can be harnessed for cryptographic applications. From 70 minutes to 75 minutes of the video, Professor Paar delves into the fundamental concept of equivalence classes, specifically focusing on modular arithmetic with a modulus of 5. He elaborates on the partitioning of integers into distinct equivalence classes, where each class comprises numbers that yield identical remainders upon division by the modulus. To illustrate, he notes that numbers like 0, 5, 10, -5, and -10 all reside within the same equivalence class modulo 5 due to their shared remainder of 0. Professor Paar further elucidates that these equivalence classes exhibit infinite cardinality, and collectively, they encompass the entirety of the integer set. He then underscores the critical role of equivalence classes in cryptographic systems, particularly within the framework of asymmetric cryptography. He emphasizes that modular arithmetic calculations often benefit from replacing numbers with their corresponding representatives within their respective equivalence classes. As an example, he demonstrates that the computation 13 by 16 8 in modular arithmetic with a modulus of 5 can be simplified by substituting 13 with 3, 16 with 1, and 8 with 3, resulting in 3 by 1 3 modulo 5. Professor Paar proceeds to explicate the concept of closure, a key property inherent in these computations. Closure signifies that any arithmetic operation performed within an equivalence class invariably produces a result that remains confined to that class. This principle ensures that computations remain within the predefined set, preventing deviations during calculations. He introduces the notion of a neutral element, an element within the equivalence class that leaves the result of an operation unchanged. In modular arithmetic, 0 serves as the neutral element for addition, while 1 fulfills this role for multiplication. Professor Paar concludes this segment by emphasizing the significance of the inverse element within an equivalence class. He defines the inverse of an element as another element that, when combined with the original element via the designated operation, generates the neutral element. For instance, the inverse of 2 in the equivalence class modulo 9 is 5, since 2 times 5 is equal to 10, and 10 modulo 9 is 1, the neutral element for multiplication. This concept plays a vital role in cryptographic operations, particularly in decryption. From 75 minutes to 80 minutes of the video, the speaker delves into the critical role of modular arithmetic within the domain of modern cryptography. He underscores that real-world cryptographic operations are almost exclusively conducted within finite sets, thereby mandating the utilization of modular arithmetic for effective computations. The speaker elucidates the fundamental nature of the modulo operator, which effectively determines the residual value, or remainder, after division. He proceeds to introduce the concept of equivalence classes in modular arithmetic, demonstrating how distinct integers can be grouped into distinct classes based on their remainders when divided by a designated modulus. The speaker then provides a concrete example using the modulus 5, showcasing how numbers such as 0, 5, 10, and so forth are all members of the same equivalence class. He effectively bridges the gap between theoretical concepts and practical applications by demonstrating how this principle manifests in cryptographic operations, where numbers are frequently reduced using the modulo operator. From 80 minutes to 85 minutes of the video, the speaker transitions from a practical demonstration of modular arithmetic to a more abstract, algebraic perspective. He introduces the concept of a ring, a fundamental algebraic structure characterized by two binary operations, addition and multiplication. A ring exhibits closure under these operations, meaning that the result of adding or multiplying any two elements within the ring will always be another element within the same ring. This closure property is crucial for maintaining consistency and predictability in algebraic operations. The speaker emphasizes that the modular operator, a key tool in modular arithmetic, inherently ensures closure by reducing any result to a value within the specified modulus. He then delves into the concept of inverses within rings, explaining that an element within a ring has an inverse with respect to multiplication only if the greatest common divisor, GCD, of that element and the modulus is 1. This GCD condition is a prerequisite for the existence of an inverse element. To illustrate, he considers the number 2 in the ring with a modulus of 9. Since the GCD of 2 and 9 is 1, the inverse of 2 exists within this ring. To find this inverse, we must solve the modular equation 2 * x equals 1 mod 9, which yields x equals 5 as the inverse of 2. The speaker further explores the implications of these concepts in the context of cryptographic systems. He reveals that due to the existence of inverses within rings, any representative of an equivalence class can be utilized for computations in modular arithmetic. This allows for greater flexibility, as we can substitute an original number with an equivalent value within its equivalence class, simplifying calculations, especially when dealing with large numbers. This property is instrumental in optimizing cryptographic algorithms. The speaker concludes this segment by highlighting the significance of modular arithmetic in cryptography. He emphasizes that these concepts will form a crucial foundation for understanding more complex and sophisticated cryptographic algorithms that will be discussed in future lectures. Modular arithmetic remains a fundamental tool in cryptography, and its importance will become increasingly evident as the course progresses. From 85 minutes to 90 minutes of the video, the speaker delves deeper into modular arithmetic, emphasizing its fundamental role in applied cryptography. He introduces the concept of equivalence classes, illustrating that the residue resulting from a modulo operation is not always singular. To demonstrate this point, he offers an example where 42 modulo 9 can yield multiple remainders, 4, 6, and -3. The speaker then introduces the key space, defined as the collection of all potential keys within a cryptosystem. He explains that the key space can be determined by calculating the product of the possible values for the key components A and B. In the presented example, where A can assume 12 distinct values and B can assume 26 distinct values, the resulting key space is 12 times 26 equals 312. The speaker underscores the pivotal role of equivalence classes in cryptographic algorithms, particularly when addressing computationally intensive operations involving large numbers. He posits that leveraging equivalence classes provides a mechanism for efficiently managing these operations by reducing large numbers to their equivalent representations within a smaller set. From 90 minutes to 91 minutes of the video, Professor Paar elucidates the concept of equivalence classes in modular arithmetic, emphasizing the non-uniqueness of remainders. He illustrates this with the example of 42 modulo 9, demonstrating how remainders of both 6 and -3 satisfy the definition. He then transitions into a discussion of rings, mathematical structures characterized by the presence of two operations, addition and multiplication. He cites the set of integers modulo 5 as an exemplar, wherein the addition and multiplication of integers modulo 5 invariably yield another integer modulo 5. Professor Paar emphasizes the crucial role of the greatest common divisor, GCD, in determining the existence of inverses within a ring. He illustrates this with the example of 2 modulo 9, where the GCD of 2 and 9 being 1 establishes the existence of an inverse, which is 5. In conclusion, he highlights the AIN cipher, which leverages two keys, A and B, for encrypting a letter, thereby expanding the key space. He underscores that decryption in this cipher entails multiplying the ciphertext by the inverse of a modulo 26.